Okay, so welcome back to today's, or rather this week's last lecture. So today we have Professor Rongchan from Beijing Institute of Technology. So Rongchan defended her thesis from Chinese Academy of Sciences and University of Bielefeld in 2012, and then she moved to Beijing Institute of Technology, where she has currently this position of professor. So, she is going to talk about today non-unique ergodicity for deterministic and stochastic Navier-Stokes equations. So, Rongchan, floor is all yours.
Okay. Thank you very much for this kind invitation and introduction. Okay, my talk will based on our recent joint work with Martina Hoffmanova and Xiangchan Zhu. And my talk will be divided into the following 4 parts. The first part, I will introduce some backgrounds for this stochastic, Navier-Stokes, and Euler equations. The second part I will also recall. Here is also include this Navier-Stokes equation and Euler equations driven by trace class noise. This is some noise, just a function valued noise. But in time direction, for time arrival, it's still a distribution. It's just the time derivative of the Brown motion. And the third part is the main part of my talk. Is about this non-uniqueness of the stationary solutions for both the stochastic, Navier-Stokes, and Euler equations. The last part, I will go to some singular Navier-Stokes equations, just about this Navier-Stokes equations driven by singular noise, since we find this convex integration method can help us to construct global solutions for even the Navier-Stokes equation driven by very singular noise. So let's go to this first part. We will consider this Navier-Stokes equations and our Euler equation on the 3-dimensional torus. And here this U we denote this velocity field and time t and position x, and P is the pressure term, and this nu is viscosity constant here. And for this nu strictly positive, so this corresponding to this Navier-Stokes system. And when nu equals to 0, so this is Euler equations. And the driven noise is we consider this F is some random noise, and you also satisfy divergence-free condition. And this is our model. And to derive such kind of model just follows by Newton's law. So we consider this U is this velocity field depending on time t and position x. And if we take in time derivative for the velocity, we give the force. And on one hand, we can get this variation part depending on time, the time derivatives. And we also get this convection terms coming from this partial derivative for this position part. And also then taking the time derivative for this position part. And on the right hand side, we give the force term. With one part, it comes from the diffusion part, which is depending on the viscosity constant nu here. And also the internal source, this is the gradient of the pressure part. And the other part is the external source. This F can be viewed, the random noise can be viewed as some external source. And we also, the solution of this Navier-Stokes equation should satisfy also this mass conservation. So if the rho is the density of the fluid, using this mass conservation, we see that if rho is a constant, then we can see this divergence-free condition. So this is the simple derivation of this Navier-Stokes system. And now in our case, we were mainly concentrated on adding the stochastic force. So the motivation for adding such kind of force, one is so-called this stochastic reduction. So this just means when we deriving this kind of models, in general, we will overlook some error part. and we have a lot of error part. By using this central limit theory, we know that all the effect of the error part will give us some like Gaussian type of noise. So this is the one motivation we add the Euler common noise is the time derivatives of the Euler this Brown emotion. The second motivation is so-called this regularization by noise. So this just means if we add in suitable noise for the system, this may get some good effect for the properties of the solutions. For example, if we intuitively, if we add in more noise, for example, like the space-time white noise, if we consider related chromography equations, this kind of space-time white noise will give us second-order derivatives. This gives us some elliptic operators on the whole on the infinite dimensional space. So this may give some smoothing effect for the behavior of the solutions. And also recent work by this Frandoli and De Junlo, they can also see the transport type of noise can also help to give some also prevents the blow up of the solutions to the Navier-Stokes system. And we also have a work long time ago, several years ago, to say the linear multiplicative noise can also prevent the solution blow up with a large probability. And the third motivation is related to the turbulence phenomenon. For this turbulence, from experiment, people find if we want to understand the dynamic behavior of this turbulence, it's very sensitive with respect to this initial data and boundary conditions. And people may think this may satisfy some statistical law. So this is to have this statistical law. It's believed that there's some probability law of the solution. So to have this probability law, maybe it's natural to add the noise for the solutions, for the equation, or consider some stochastic solution or random solutions to even the deterministic equations. And this is also related to this Kolmogor's 1941 turbulence theory. And here I also get a picture. This is from the book for this turbulence phenomenon. If we consider this is this line is like some fluid, if they cross some like a cylinder or some barriers, and the behavior of this turbulence also related to this real numbers, and it's related to the viscosity constant of the fluid. So intuitively, if the viscosity constant is very large, so this is like this fluid is like some honey. So even we we have a barrier or cylinder here, the fluid go across it, the behavior of this fluid will not change too much. But if the Reynolds number becomes larger and larger, we can see this turbulence phenomenon disappear here. So when this nu goes to infinity, this is a high Reynolds number limit. This is also this highly turbulent regime in this case. This is the motivation to study this kind of models. And before, I also want to recall some results from this deterministic Navier-Stokes system. For the deterministic Navier-Stokes system, there are a lot of literatures to study, to develop the solution theory for this deterministic Navier-Stokes system. One famous result is by this Laray's work, they can obtain the global existence of weak solutions for all dimensional case. And if the initial data is small in some in suitable space, in some Basel space, or even other space, or Sobolev space, there's a result by this Kato and Fujita. They can obtain the existence and the smoothness of global solutions. But for general initial data, this kind of result is still an big open problems. But on the other hand, since this weak solutions exist for all dimensional case, so it's natural to ask whether this kind of weak solution is unique or not unique. And breakthrough work is due to this Bookmaster and Vickers work. They are based on this the Lely and Hindis convex integration method. Based on these techniques, they can first prove the non-uniqueness of this analytic weak solutions to this deterministic Navier-Stokes system. And they can construct solutions with a given energy. So in this case, by choosing different energy, the solution is should be not unique. And furthermore, they can even do joint with Colombo. They can connect and choose local strong solutions to Navier-Stokes system by using also using this convex integration method. And however, this solution to Navier-Stokes system by this convex integration is not does not satisfy this energy inequality. So more recently, by this Arbitrium, Brew, and Colombo, they can even prove the non-uniqueness of these Larray solutions, but for some force. This is their recent work. And in this, for the deterministic case, to understand the lotion of the solutions, the regularity of the solution is very important. If the solution have high regularities, they are smooth enough, they can be called like the strong solutions or smooth solutions. If the solution is in some states, just in some weaker space, just have some in some L2 space and with lower order regularities in some H zeta space for zeta smaller than 1. So this is called some weak solutions. This is for the deterministic case. But for in the stochastic setting, since we have noise, we need to understand to build this mathematical model for the stochastic noise. So in this case, in fact, we have more structure of the equations, and we also have more structures for the more definition, more notions of the solutions in the stochastic setting. In the second part, I will talk about this Navier-Stokes equations or even Euler equations driven by this trace class type of noise. So in this case, we have different notion of the solutions. One is so-called this martingale solutions. So this martingale solutions, you can view it as the law of the this just gives us the law of the solutions. So this just means we have the probability measure on the canonic space. For example, for Navier-Stokes system, we can choose this canonic space is a continuous path taking values in this -3 space. And the canonical process under this probability measure should satisfy the related martingale problems. So this is so-called this martingale solutions. And this is equivalent to this so-called this probabilistic weak solutions. So this probabilistic weak just means we can construct a stochastic basis. We can construct probability space and also construct the noise and also the solutions live on this probability space such that the solution will satisfy the equation. So this just means we need to construct a probability space and also the noise part. So this is the notion of the martingale solutions. And also this is just gives the law of the solutions. But for this correspondingly, we also have so-called this probabilistic, this strong solutions. So this strong, just this kind of notion of the solution, probabilistic strong solution, is similar as the solution in the PDE sense, in the deterministic sense. So this just means we can construct for fixed stochastic basis and the given noise, we can find a solution, which in fact can be written as a measurable map of the solutions, such that we can construct the solutions pathwisely, such that the solution will satisfy the equation on the given probability space and for the given noise. And to construct this kind of solution, in general, we need the solution need to be adapted to the filtration generated by the noise. So this just means the solution for fixed time t, the solution should only depending on the noise before time, only depending on the information given by the noise before time t. So this is called this probabilistic strong solution. So you can think this probabilistic strong solution can be seen with the noise and some input, and we fix the noise, we can construct the solutions. So this is like the PDE deterministic case of the solution, but the martingale solution is is weaker. We only have the law of the solutions on this canonic space. And in this case, we can say the law of the and to realize the solution, we need to construct a new probability space and find the noise, and such that the solution satisfies the equation. And the relation, as we mentioned, so this probabilistic strong solution is stronger than this martingale solutions. And their relation is due to the following. This is famous, this Yamada-Watanabe's theorem in the stochastic analysis. So this means if we have this martingale solutions, and also this pathwise uniqueness results, then we can construct this probabilistic strong solutions. So since if we have uniqueness, then we can identify the solutions as the measurable map of the noise. So this gives us the solution can be only depending on the information of the noise before time t. So it should be probabilistic strong. And on the other hand, if we have a probabilistic strong solution, and if the law of the solution are unique, this also implies the pathwise uniqueness. And here, this pathwise uniqueness, you can view it as a similar notion of this uniqueness in the deterministic setting. So this means for almost every path, the solution should be the same. But the uniqueness in law, we can say, since this are a weaker notion in this case. And for the 3D Navier-Stokes equations, the lower results is for the stochastic 3D Navier-Stokes equation, the Lorraine-Martingale solutions, and it's also Markov solutions, have been constructed by Flandoli and Romito in more than 10 years ago. Here, this Martingale solutions can be also viewed as this weak solutions, probably weak solutions in this stochastic setting. And now we want to go to our first result in these directions. So now for the PDE results, we already have this non-uniqueness of these solutions to the Navier-Stokes system. So it's natural to ask whether we can, so this pathwise non-uniqueness should hold in this sense. But as I mentioned, this uniqueness is in law is weaker than this pathwise uniqueness. So non-uniqueness in law is stronger than this pathwise non-uniqueness. So in this case, our first question is to, when we learn this convex integration method, we want to understand whether we can obtain this non-uniqueness in law still holds in this stochastic setting. And in this case, I also want to mention two type of results in the stochastic setting, just for this ODE and SDE case. One is so-called this regularization by noise effect, as I just mentioned before. This means if for this kind of ODE, even starting from 0 initial data, since this alpha is smaller than 1, so it can have infinite many solutions. But if we add the Brown emotion and the noise, we can prove this kind of SDE has a unique probabilistic strong solutions. So this we can see the regularization by noise effect from this additive noise here. So in our case, due to this regularization by noise effect, we first ask if we add the noise, whether this non-uniqueness still holds in the stochastic setting. The second example is also SDE. And for this kind of SDE, this pathwise uniqueness does not hold, since if X is the solutions, the minus X is also another solutions. So this means the pathwise uniqueness will not hold for the solution even starting from the same initial data 0. However, the uniqueness in law will still hold for this kind of solutions XT. So we'll also ask whether we can obtain this non-uniqueness in law in this setting. And our first work in this directions is we can obtain for the stochastic 3D Navier-Stokes equations, our Euler system, we can obtain this non-uniqueness in law. In fact, based on this convex integration method, we can construct the solutions for this Navier-Stokes system which will not satisfy the S energy inequality. And we compare this solution with the slurry solutions, since this slurry solution satisfy energy inequalities. And we use this notion martingale solutions, and we can finally derive this non-uniqueness in law hold for the stochastic setting. And also for this Euler equations, we can even do more based on this original result by Delalis and Hindis, their construction based on this convex integration method. We can even prove infinite many solutions satisfy energy inequalities, but the non-uniqueness in law still hold in this stochastic Euler setting. So this is the first question we want to study. And when we learn this convex integration method, we find this is also a very interesting new idea, a new approach to construct the solutions. In general, when we do this stochastic Navier-Stokes system, or this stochastic Euler equations, we construct the solution. One is by using this energy method. So we need to have some energy inequality, and this gives us some uniform bonds. And then by compactness argument, we can construct the solutions. We can construct the martingale solutions. This is one method. The other method is to using some fixed point argument. We can construct some like local in time solutions to construct the solutions before some stopping time, some random time, something like that. But this convex integration, by using this iteration method during each iteration, they will construct some building block, adding this building block. So this is more construct solutions in a more constructive way. And based on this kind of approach, we want to study the global existence of this probabilistic strong solution. I know this problem when I did my PhD study in Bielefeld University. My supervisor always asked whether we can construct probabilistic strong solutions to this stochastic 3D Navier-Stokes system. But they have idea for like this regularization by noise, as I just mentioned by this Yamada-Watanabe theorem. If we have a chance to construct this probabilistic strong solution, and we can, if we have some chance to prove uniqueness in law, finally this may help to understand this pathwise uniqueness of this Navier-Stokes system. However, in general, to construct this probabilistic strong solution, the Euler method is first to prove this pathwise uniqueness. There's seems no other method to, without uniqueness, how to construct it is still unclear. The main difficulty, in fact, comes from control the noise part. In general, to control the noise, one method is to take in the expectation to control the stochastic integral. So this will finally give us this so-called martingale solution, or this so-called probabilistic weak solution. However, this will cannot produce this probabilistic strong solution, since now we will destroy the adaptedness for, we cannot deduce the adaptedness for the solutions for given noise. And another method is to transform this stochastic equation to a random PDE and control everything omega-wise, and also using so-called this compactness argument. However, since here we don't have uniqueness of the solutions, so we can also not derive this adaptiveness result. This adaptiveness, we need for any fixed time t, the solution should only depending on the information of the noise before time t. In general, we can do some variable selection, but if we want to do it for every time t, since time is uncountable set, so it's cannot be done easily. But for this convex integration method, this gives us a new way to construct the solutions. So in this case, we can, for every initial data in L2, and satisfy divergence-free condition, we can also construct this infinitely probabilistic strong solutions, and also they are if we analyze the regularity, it's just analytical weak solutions in this case. And we can also do more to study the properties of the solutions in the stochastic setting, like this long-time behavior of the solutions. One notion is the so-called marker property of the solutions. In the deterministic setting, if the solution have the uniqueness, so the solution will satisfy some flow properties. But in the stochastic setting, if we have uniqueness properties, the solution in general it will satisfy this flow properties in law. So this flow property in law will can be viewed as this marker property. In the stochastic setting for the 3D Navier-Stokes system, in general, we don't have this flow, we don't have this uniqueness result. So how to, but we still can do some Markov selection to construct a Markov process. But in this case, we can also using this convex integration method to say even this Markov solutions are not unique. So we can have different Markov semigroup for this stochastic Navier-Stokes system. And this Markov semigroup is also a useful tool to study the long-time behaviors of this stochastic Navier-Stokes system. And this is also related to this so-called this ergodicity hypothesis in this turbulence theory. So this is the basic assumptions in this turbulence theory. So this just means the time average of these solutions will converge to this convergence to a probability. The law of this time average of the solution will convergence to a probability measure. And in fact, this measure is should be invariant, and also gives gives us statistical stationary solutions. So this just means we can see the law of the solutions will not change if we shift the time of the solutions. And we can see in one case we can only consider the marginal law of the solution for fixed time t. We can also consider the law of the whole path of the solutions. And if we shift the path, the law will also not change. So this is so-called statistical stationary solution. And the ergodic stationary solution just means the time average of the solution, the law of the time average of the solution will convergence to the marginal law of the solutions. And by the ergodic theory, for a dynamic system, we know the ergodic stationary solution should be all these stationary solutions will form a convex set, closed convex set, and the ergodic stationary solution, in fact, are the extreme points of this convex set. So if we know the existence of this stationary solutions, we can also find some ergodic stationary solutions. And this is the basic assumption. And as I just mentioned, we have the non-uniqueness of Markov solutions. And in general, for fixed Markov solutions, in the stochastic setting, there are many people to study the long-time behavior of this Markov solutions. One famous result is to consider 2D stochastic Navier-Stokes system. And they can obtain the uniqueness of this invariant measures if the driven noise is very degenerate. So in general, if we have more noise, so the solution may go around everywhere. So this is more likely we have this uniqueness of invariant measure. But in the result, they say even we only have 4 directions have the measures, the solution, the invariant measure is also not unique. But for the 3-dimensional case, since we don't know whether we have uniqueness, so result is due to Daprato and Debush and also Flandoli and Omito, they can obtain if the driven noise is non-degenerate. So for every Markov selection, so they can find construct a Markov process. Every Markov selection will have a unique invariant measure. So as I just mentioned, their result is for every Markov selection have a unique invariant measure. Now we can prove the Markov semigroup is not unique. So our next question is whether this invariant measure or this stationary measure should be unique. So this is our the main part of this talk, the third part of this talk. We will concentrate on this non-uniqueness of this stationary solutions for this stochastic Navier-Stokes or this Euler equations in this setting. So this is related to our third problem. One more thing is whether we can construct non-uniqueness of the stationary solutions for stochastic Navier-Stokes system. The other thing is for this stochastic Euler equations, there's even in the literature, it's still unknown whether there exists a stationary solutions to this stochastic Euler equations due to their for this Euler system there's lack of this uniform dissipation due to disappearance of this Laplacian operator. So in our case, we also using this convex integration method. We can obtain the existence of infinite many stationary solutions. And I just mentioned, since this all these stationary solutions to this Navier-Stokes or Euler equations, they form a convex set. So if we go to this extreme points of this convex set, we get this ergodic stationary solutions in this setting to both this stochastic 3D Navier-Stokes and Euler equations in this sense. And this is for this stationary solution. And furthermore, we can also consider this violation viscosity limit. On one side, if nu1 goes to 0, we can find stationary solutions un with the viscosity constant given by nu1, such that first the law of this un is tight. So this we can, after we know the law of this un is tight, we can use this compactness argument. And then we can see every tight limit gives a solution, stationary solutions to this stochastic Euler equations. This is if we starting from the, we can always find the for any valuation limit nu1, we can always find the stationary solution of un such that the limit accumulate every tight limit is a stationary solution to this stochastic Euler equations. And on the other hand, if we just starting from the stationary solutions to the stochastic Euler equations, but here we also need to assume the stationary solutions of these Euler equations satisfy suitable moments bound. Then we can also prove, we can also construct the stationary solutions to the stochastic Euler equations. Such that this stationary solution to the Navier-Stokes system, such that this solutions to Euler equation can be viewed as the limit of the law of the stationary solutions to the Navier-Stokes system. So this means for every given stationary solutions to this stochastic Euler equations, the law of it can be viewed as the limit of the law of the stationary solutions to this stochastic Navier-Stokes system. So this is we can first construct this stationary solutions to the stochastic 3D Euler equations. On the other hand, this also helps us to study this violation viscosity limit in the stationary setting. And on the other hand, we can also study the case for the relation between the stochastic setting and the deterministic setting. Many people believe if we want to produce random solutions for the deterministic Navier-Stokes or deterministic Euler equation, we may this may come from to taking this violation noise part. So in this case, we can consider gamma n is a sequence goes to 0. And here we also fix a stationary random stationary stochastic process with suitable moments bounds. So in this case, you can just view they can be some stationary process can be viewed also as the Gaussian a suitable Gaussian process. And here this moments bound assumption will satisfied by a Gaussian process. And you can also choose some other stationary solution or other stationary process with bounded omega y's, then you can also, this condition can also be easily checked. Then we can construct solutions to this stochastic Navier-Stokes system such that the law of this U1 is tight. So this tight just means then we can take in the limit along a subsequence. Then every tight limit is also a stationary solutions to the deterministic Navier-Stokes or this Euler system. And furthermore, this every tight limit, we can also prove it should be close to this Z, the stationary process Z, in this W11 norm, can be close to it for any given epsilon. So this just means our U, this stochastic, our every tight limit of this U, should be given, it should be random. It's not a deterministic solution, even for deterministic Navier-Stokes or Euler system. And this can also come from this valuation, this noise part. And since it can also close to even can close to be a Gaussian process in this setting. And also close to this all other stationary stochastic process. This is this relation between this stochastic Navier-Stokes system and the deterministic setting in the stationary stationary case. And in the following, I want to explain a little bit how we derive this kind of results in the stochastic setting. In general, okay, I also want to mention with my PhD student, we can improve the regularities for the stochastic Euler equations. So we can also construct the stationary solutions to stochastic Euler equations such that the solution stay in some Holder space. But here we cannot go to this this Onsager, this regime, this is 1/3 minus regime, and in this case, our Holder exponent is still very small in this setting. And now I want to explain a little bit the idea of our proof, how we get this kind of results. In fact, to construct these stationary solutions, we need some moments bounds for these solutions. So in this case, we need to develop the idea is to develop a stochastic convex integration method. So this just means if we calculate the U is our solutions, we want the solution if we calculate it in some Sobolev space H zeta, and also have some Holder regularity on time, and the higher moment of this 2R moment of the solutions should be uniform bound. And here we need to the solution should be independent of this shift of the path. So this UT we always view it as a path on the whole line, and this moment bound should be independent of the shifter path. And to take in the valuation viscosity constant, we also want this bound should be uniform with respect to this nu here. And to derive such kind of bounds in general, to control the noise part, one method is to use this Ito formula and to use this martingale approach to control the noise. But for the convex integration, since it's an iteration scheme, so in general, we will decompose this using this so-called Laplace and Debush trick to decompose this U into the following two parts. The first part is the linear part. So this means this will satisfy these linear equations. So, and the second part V will satisfy these nonlinear equations. So the advantage is this Z is just the linear equations. So and we take Z as the stationary solutions. So Z will satisfy the following moments bound since Z is just a Gaussian process. And the equation for this V looks more complicated, but in fact, we will not see the noise part. All these terms appears in this V equations is a function with respect to time. But here the time derivative of the Brown motion is not it's not a function. So in this case, now we have better regularity for this Z part. And we want to using this moments bound to obtain this suitable moments bound for this V part. And I want and our idea is still to do this convex integration for this V component. So this is like this iteration scheme we learn from this their Delay and Jacqueline Hindy's famous work. And here this Q is the iteration in this Q step. And this RQ is this Reynolds stress. And then the idea for this convex integration is if we want to start from this Q step to Q plus 1 step, we don't do using some fixed point to find from Q step to Q plus 1 step. But on the other hand, here in this case, we need to construct a suitable this build WQ plus 1 part. From Q step to Q plus 1 step. And the main idea you already hear in the previous talk is in this case is to choose suitable WQ plus 1 such that if we substitute this kind of WQ plus 1 for this Reynolds stress, this can be viewed as some error part. And we will see this nonlinearity will cancel this RQ term. So in this case, this part will become smaller. So in this case, then the whole RQ plus 1 part will also become smaller and smaller. So finally, this Reynolds stress will goes to 0. We find the solution. And in our case, we always choose this WQ plus 1 is like this XI part. XI is some this will similar from this Reynolds stress, so this will oscillate slowly. And this WXI will always take this intermittent jets from this Buckmaster-Colombo-Wickels constructions for this Navier-Stokes system. So if we want to go to Euler Stochastic Euler equations, we need to take in other building blocks. And in this case, since this WXI have this intermittent property, so this means this space concentration will ensure the linear error is very small in L1 norm. So this finally helps us to prove all this error part will go to slowly, will go to 0 with respect to L1 norm. And in our case, to do this stochastic convex integration, we want to get such kind of moments bound for this VQ uniformly in Q. And our previous work, as I just mentioned, for this problem 1 and problem 2, we're using this, we always control the noise by using some stopping time. So this is means we will choose a suitable stopping time to control the growth of suitable norm of the noise. But if we want to construct the stationary solution, this is like the long time behaviors of the solution. This stopping time is not good enough for these stationary solutions. So in this case, we want to overcome this stopping time. We want to do this iteration involving this stochastic calculation using this taking expectation during this iteration. However, in this case, this our system is non-quadratic, so this estimate should be superlinear. In this case, we should control all the moments. So for this iterative estimate, we will need 2 types of bounds. One bound is lower moments for some fixed R. this part for this RQ part, this kind of moments bound should goes to 0. And on the other hand, we want some higher moments bound, this RQ to for the NAM, will allow this kind of moments bound may have some blow up. But finally, we can also still using the building block intermittent properties, and by choosing suitable parameters like this lambda Q increase very fast, we can absorb this blow up. So this finally we can construct the solution have this uniform moments bounds, and this helps us to construct a stationary solution. And on the other hand, in a general setting for the Markov semigroup, to construct the stationary solution or invariant measure, the Euler argument is so-called this Krylov-Berger-Liouville argument. So this means if you have the Markov semigroup and you can obtain the solution have a uniform in time bounds, then we can construct the stationary invariant measure or stationary solutions. But in general, to prove this argument, we are using the so-called Feller properties of the related Markov semigroup. So this just means this Markov semigroup should map a continuous function to also a continuous function. So in general, to prove this Feller property, we need the solutions is continuous with respect to the initial data. So this is in some sense is even stronger than uniqueness property. But in this case, we don't have such kind of properties. So instead of consider this Markov semigroup, we will work with some shifts just on this path space. We will consider the path space. One is for the solution, the other is for the Brown motion part. And we will also consider Euler shifts on the path space. One is for the just the shift solution, and also shift the Brown motion part. Since here this Brown motion have the independent increment, so we shift this Brown motion part in this sense. And then our moments bound are good enough to apply this Krylov-Berger-Liouville method. So this helps us to using the law of, in fact, the integration of this time average for this shift of the solution can converge to the, we can use it to find the stationary solutions. And this gives us the limiting law gives us stationary solutions in this setting. And furthermore, we can using this, as I just mentioned, by using this Krein-Milman's argument, we can find this ergodic stationary solution, since they are just the extreme points of all the stationary solutions. And here we understand this ergodicity in terms of this dynamic system, not in terms of this Markov semigroup. And here we also have this non-uniqueness of this stationary solution by choosing different energy. And since our bounds is uniform in nu, in this viscosity constant, so we can also apply our results to the stochastic Euler equations and also this valuation viscosity limit in this setting. So this is the main parts of my talk about this non-uniqueness of the stationary solutions. And all this part is about the solution series if the Navier-Stokes system or Euler system perturbed by some so-called this trace class noise. So this trace class noise just means the noise if on the time variable it's usually it's very rough. It's not a function. It's just a time derivative of Brown motion. But in the spatial variable, it should always be a function or some nice functions. But recently in the for the SPD, there are a lot of people interested in if the SPD or PDE perturbed by some singular noise. For example, so-called space-time white noise. And in our case, we want to also in the last part of my talk, maybe 10 minutes, I will shortly talk a little bit. We can use this convex integration method to construct global solutions to this Navier-Stokes system driven by this singular noise. So maybe I first recall what is the singular noise, this space-time white noise. So we also consider our Navier-Stokes system. And our driven noise is so-called space-time white noise. So space-time white noise is just you can view it as some random Gaussian distribution with respect to time and space. And the correlation function is mean zero, and the correlation function given by the Dirac functions. So we already know the Dirac function is a distribution, not a function. So in this case, the regularity, if we counting the regularity of this space-time white noise, it's also not a function, it's just a distribution. So regularity for this size in C minus D over 2 minus 1 minus space. And so this is we calculate in some parabolic scaling. So if dimension is higher, the space-time white noise will become even more rough. And the last minus is minus delta for any delta bigger than 0. And we recall result from harmonic analysis. If we want to give a meaning of the product of one function and one distribution, one is in C alpha space and the other is in C beta space, we always need this alpha plus beta bigger than 0. However, due to this space-time white noise, even we have this shorter estimate, we can see now the solution U in two-dimensional case, Xi is in C minus 2 minus space. So the regularity for this U is also only in C minus. So how to make sense of this nonlinearity should be a problem. And 20 years ago, by Deplatte and Debush, they developed the so-called this Deplatte and Debush trick. They can decompose this as what I'm already mentioned for this. We already use for this convex integration scheme for this Navier-Stokes stochastic Navier-Stokes system. Now, in this case, we can decompose this U to the two parts. One is the linear part, the other is this nonlinear part. The advantage is now, here we know it's a Gaussian. We can use the so-called weak product to make sense of this nonlinearity. And this one is also in C minor space. But now the regularity for V, you can calculate the regularity. It's even better. It's in C1 minor space. So we can go to a better space. Now, so then using the fixed point argument in this beta project bush, they can get a local repulsiveness of the solutions. And furthermore, since this Navier-Stokes system, we have the Gaussian free field as since as the invariant measure, so we can get to the global solutions by using invariant measure, starting almost from every point. But we can using strong failure to get to this. This is like this Begins argument to construct the global solutions. But we can do more. We can also use strong failure property of the related macro semigroup to get to the even global solution starting from every initial data. However, we still want a pure PDE argument to derive the global solutions. And for two-dimensional case, we thought this problem for a long time, but we didn't know how to solve it. Even we know for the Navier-Stokes system, we have this energy estimate, but due to the singularity of this Z, this will stop this energy inequality. But finally, recently, by Higher and Rosati, they can solve this problem by PDE argument. But their technique only works for 2D. But for three-dimensional case, even local solution theory, there's some problem. In fact, this Z will stays in a verse space. And even we do this dot product and Debussy trick again, we always have these red terms. And this red term, even we do this trick again and again, this will not improve this regularity. And this H always in this C1 half minor space. So this red term cannot make sense in the classical setting, even we do this trick again. So the solution, one solution is by this highest regularized structure theory, or this parallel control distribution method proposed by Gubinana, Imkela, and Pakrovsky. We can obtain the local equivalence of this 3D Navier-Stokes equation driven by space-time white noise. However, this kind of, if we want to construct global solutions, as I just mentioned, the race work, we can always use the energy estimate to construct the global solutions. But to do it for 3D, to extend the highest work, Rosati's work to 3D, it's still unknown. This technique, so this is for singular SPD. A common general question is how to derive global solution while uniform estimate. Yeah, we have similar models like so-called this dynamic 5-4 model or this KPZ equations. And for this kind of model, we have some dissipation from nonlinearity, or we can use suitable transform, but or using maximum principle. But for Navier-Stokes system, all these techniques breaks down. The only technique we can expect is this L2 energy estimate. However, this does not work here. But then later we learn this convex integration method, or even using this Begins argument of this using invariant measure. But the existence of invariant measure is still unknown. But in our case, we use this convex integration. Finally, we can still construct global solutions. So our result is for any initial data, U0, in L2 space or in this spatial space, we can find the existence infinite many, also global in time and probabilistic strong solutions. So this Navier-Stokes system driven by this space-time white noise, driven by space-time white noise. But here we need to understand the solution in a parallel controlled setting. So in fact, we need to give a meaning to this nonlinearity by using this parallel controlled calculus. So our idea is to decompose this system by using some localizer and Bonni's parallel product to some irregular part and irregular part. And we're using this parallel control calculus and a Sheldrake estimator for this irregular part, and also using convex integration for the regular part. So finally, this helps us to construct the global solutions. And this method can also be used to cover the whole regime, also from this trace class noise to this space-time white noise regime. And this is all I want to say here. And thank you for your attention. Thank you.
So thank you, Rongchan, for this beautiful talk. Are there questions or comments?
Thanks for the nice talk. I actually have two questions, but perhaps I can start with one. So you mentioned that you have the law of heavy stationary solution to the stochastic Euler equation can be viewed as an implicit limit to stationary solution to Navier-Stokes, as far as I understood. Stochastic Navier-Stokes.
You mean this?
Yes, I think it's much.
You mean this result, right?
I think no, the one before. The one before. Thanks.
Okay. This one.
Exactly, this one, exactly.
Okay, okay.
When you talk about stationary solution to stochastic Euler, since you are pumping energy with the noise, right? As far as I understand, this means that must be an anomalous dissipation mechanism. Is that true? Or am I forgetting something? Or am I... Because formally speaking, I guess the energy should grow, right? Or if I'm pumping, if there is...
In fact, this energy is constant because it's stationary, right?
No, I see. But what I want to say is that if formally the solution were smooth, which perhaps is not the case, can you show, perhaps I lost one point. Could you show the stochastic Euler equations before, just to make sure perhaps one slide before, or
Which one do you mean?
the form of the equation, if you have it.
Oh, equation. Our equation is just adding the additive noise, I think, mainly. But we can also involve other type of
Okay.
noise.
Yeah, no, so my point is, if it is just Euler equation, if there is no force, energy is formally preserved. Of course, we know that this is not true, and if you add force, formally expect the energy to growth. The fact that you are saying that there is a stationary solution to Euler, as far as I understand, stochastic Euler, means that you have some form of anomalous dissipation. Now my question is, if I understand correctly, whether, since they are solution to stationary solution, no, but that's okay. If there are solution to stochastic Navier-Stokes, stationary stochastic Navier-Stokes, whether this stationary stochastic Navier-Stokes equation solution, they are kind of smooth or not.
You mean this Euler equation, right?
Yes. So you start with the solution to Euler, and then you construct as a limit of so whether this sequence is actually smooth or not.
You mean the sequence of this Navier-Stokes?
Yes.
No, it's not. So I think it's also this convex integration solution. Yeah, it's not smooth. I mean, yeah.
Okay, thanks.
Here it's like I think this kind of results in a deterministic setting has already been obtained by this Bookmaster and Wickle. But we are just extend the result in the stochastic and also stationary setting. Yeah, so every solution we construct is a convex integration solution, not this smooth solution. Yeah.
Okay, thanks. I also have another question, but perhaps, okay, can I? Yes, just a second question. Instead, you said that you can select different ergodic solutions because you can select different energy profiles.
Yeah.
Right? Are these energy can you select, are these energy profile, I mean, of course they are stationary, so on average the energy is the same, but do these solutions preserve the energy pathwise, or you can change,
for the stationary solution, I think in this case we just have these moments, yeah, just like the expectation of this energy equals to some constant. But before, to prove this non-uniqueness of this Markov solutions, we have some constructed solutions. Before some stopping time, we can prove the solution. The energy is equals to some fixed ET, yeah, pathwisely, yeah. But it's only for some short time, I think. I'm not sure whether we can do it for long time, yeah. Yeah, but this should be done. This we do it before some stopping time, yeah.
Okay, thanks.
Thank you.
So any other questions?
I have one question.
Okay.
So when you are showing the non-uniqueness of the solution, so the Holder exponent is coming the new. So how much large is it? Can we track there?
You mean this results, right?
No, that in the different one.
Which one?
Where the exponent, the new is coming. the C to the power.
Which result? You mean this one?
No. Actually, you are proving somewhere is the regularity of the solution in the Holder exponent for Navier-Stokes equations.
Yeah, but I think all this, you mean this moments bound, right?
Yes, yeah.
I think this one is always small, right? This is the convex integration regime always small, yeah.
And in the last slide, 24th slide, so when you are taking space-time noise, so can we, in the probabilistic sense, your solution is strong, but how much is the space regularity in the solution have that in space?
I think in this case, the solution is already very rough. You can see due to this space-time white noise, the best regularity we expect is only in this space. But here we will not have such kind of holder space. We will in some basal space. Our solution will finally leave some basal space because this due to we want to using this intermittent gates. So in our solution is in some b minus 1/2 minus some and but the one infinity something like that. The integrability is in some L1 something like that. Yeah.
Thank you.
Okay. Thank you.
Okay, so I have just a small technical question. Can you please, so at some point you talked about stochastic Euler in holder space, and you mentioned that the holder exponent is pretty bad. So can you please briefly mention that what are the fundamental enemies behind this gluing technique?
You mean this result?
Yeah. So why gluing doesn't work?
In our work, we also need to modify this stochastic convex integration method because to help to increase this regularity, like for this Euler system, I think their technique by this master we and I think also the lady they using this transport equation, and they can build some suitable building block and also using the solution to this using the transport equation to construct a flow, and use this flow they can they can improve the regularity of the solutions. But for this Euler equations, so this means to use this flow, we need some pathwise bounds for the solutions. But if we only go to this kind of stochastic convex integration, we cannot derive this pathwise bound. So in this case, we also need to combine this pathwise iteration. We will have allow some pathwise bounds, but which allows some blow up for the solutions, and also combine some moments bound which will go to 0. And finally we can get to the uniform I think finally we can construct the solutions to the stochastic Euler in holder space. Yeah, but I think there's still some room to improve this results. Yeah.
Okay, thank you.
Yeah, our result, yeah.
Okay, so if there are no more questions, so let's thank Rongchan once more. Thank you, Rongchan.
Okay, thank you for your invitation.